So just to go over what we covered in the last class, we saw that when we started talking about granular flows, we said when the inertial number, which is given by this formula, is much smaller than 0.1, the flows are friction dominated and we call them as slow flows. When the inertial number is much larger than 1, then it's dominated by collisions and we call those rapid flows. And in between these two, where both friction and collisions are important, we have dense flows in which perhaps there's some friction, there's some collision, both are involved. And one of the models that has turned out to be quite successful in describing this is this mu and I model. I is of course the inertial number which we just showed last in the previous slide. And what this model says is that if you look at the ratio of the shear stress to the pressure in a dense granular flow, then that is of course a dimensionless quantity and we call it as mu as a friction coefficient. This is a shear rate dependent friction coefficient, or you can say effective friction coefficient. And what in this model what is stated is that this friction coefficient depends only on the inertial number, nothing else. And they also say that the solid volume fraction also depends only on the inertial number, where mu and phi are empirical functions. That means that we have to do experiments and determine what they are. And what has been found after a lot of experimentation is that you can write this mu in this simple form where µs, µ2 and I0 are constants and I is the inertial number. So mu varies with I in this way. And if we draw this function graphically, it looks like this. When you put I equal to 0, then of course mu is equal to µs, that is this one, this value. If you put I equal to infinity, then mu is just equal to µ2. So that means as this becomes larger and larger, it asymptotes to value µ2. And if you put I equal to I0, then it turns out that mu is just equal to µs by µ2 by 2. That means if you draw a line here and a line here, and then you draw a line between them, which is corresponding to this value, then the value of I that you get is I0. So this is what it is. And also through experiments, it's found that phi is just given by some constant minus another constant times I. So here there are these two parameters. So here you have 5-parameter model, µs, µ2, I0, phi max and C. So now this is in terms of your friction coefficient and all these things. So how can we use this to solve any flow problem? Well, one thing that we saw last time is that it's easy to define the viscosity in terms of mu, because viscosity is just the shear stress by gamma dot. And from this equation, we know that the shear stress is just mu times P. So mu times P by gamma dot defines the viscosity. So once we have the viscosity, then we can easily write down the constitutive equations. But what is interesting is that you know that the shear stress doesn't go to 0 when I goes to 0. We saw that when I is equal to 0, mu is equal to µs. That means tau xy is µs times the pressure. That means it's not like in a Newtonian fluid where if shear stress is 0, I mean shear rate is 0, then shear stress also is 0. So here you have some sort of a yield stress. So now if you want to write it as in a tensor form, then the stress tensor is just given by 2 eta times d, where eta is the viscosity, d is a symmetric part of the velocity gradient tensor. But this is only true for the magnitude of the stress more than the yield stress, where the magnitude of the stress is given by this, and the yield stress is given by this, which is µs times p, as we saw in the previous slide. If this condition is not satisfied, then there is no deformation, that is d is equal to 0. And of course over here for tensor form, gamma dot is defined as 2d double dot d. So this gives us a complete set of equations for the stress. As we wrote before, here mu is also given by this, where mu s, mu2 and I0 are parameters which are known. I mean, you have to find them out from experiment. Here mu s is a parameter, and here phi max and c are parameters. So this is the constitutive model. This defines what the material properties are. And then the governing equations are that divergence of u is equal to 0. This is the continuity equation, and this is the momentum balance equation. What is interesting is, unlike in rapid flows, we don't need the granular temperature because our viscosity is written in terms of the pressure rather than the temperature. So this is what we had done last time. And let me just show you this. So this is the paper that was published in 2006, which says a constitutive law for dense granular flows. It's already got 1,000 citations, 1,000 plus citations. This means that it is quite widely used. It's used by many people. And in that paper, they showed how well the model, this is some experimental data, the dots. And the lines are the theoretical predictions for the velocity for different cases. And of course, you get quite good agreement. And this is the sort of, if you look at the system where there's sidewalls with friction, and then you're pouring things down in the middle, then you get this type of velocity profiles. This side is the velocity, this is the y coordinate, and this is the z coordinate. So this just shows that even for quite a complex flow, the model works quite well. We also, one of the students in our lab has done a lot of work on this. Now, of course, he's a professor at IIT Kanpur, Anurag Tripathi. So these are some of his PhD results. What it shows is, this is that flow down an inclined plane, very much like what the Silbert, the results I showed you last time, that you have a rough inclined plane, the particles are flowing down on this plane. And if you look at the velocity profile, it looks like this. This is exactly the Bagnol profile. And this is for different angles going from 22 to 28 like this. So as the angle increases, the velocity also increases, as we saw. The solid volume fraction is nearly constant. The shear stress increases linearly with depth. This is true for any material. We have seen this for flow down an inclined plane already. And the pressure also increases linearly with depth. This is also true for any material. Now, since we know the velocity profile, we know Vx as a function of y. So we can take the derivative of this and we get straight lines, or almost straight lines, slightly curved lines. And now we know tau xy, which is gamma dot, we know pressure. So we can easily calculate the inertial number, and this is the graph of the inertial number. And it's almost constant. And then you get this shear stress and pressure, and you can take the ratio of those two, and you can expect that you'll be able to calculate mu as well. Now, if you take data from many different simulations and put it all on one graph, then you can see this is, so all these data points, they lie exactly on this line, which we have seen. And if you look at the solid volume fraction also, it lies on this line, which is given by this equation. So basically, this model works quite well, particularly for shear flows. Today, what I'd like to do is maybe do one or two simple examples related to this mu I model. So let us go to the notes. So this is what we had done last time. And so today what we'll do is we'll start off on some examples. Okay. So today is already the 4th of October. And this is lecture number 27. Okay. So what I'd like to do today is this is exactly what we did for uh, the rapid flows, and now we want to do the same thing for this JFP fluid. The reason is this is the initials of the authors, Job, Forter, and Pulikin. That's why I call it JFP fluid. This is basically what I want to say is mu I. Okay. And so we've done this before, that let's say there is an inclined plane like this. And suppose this is our domain. We put our coordinate system here. This distance, this direction is x, this is y, and gravity is acting in the downward direction like this. Suppose this angle is theta, and we expect that there will be a flow like this down the inclined plane. Okay, and we have already essentially solved this problem where what I said, if you remember, it doesn't matter what the fluid is. For any fluid for this system, you will always have ux is equal to a function only of y. Your pressure will be given by rho b g cos theta times y, and then your shear stress will be given by minus rho b g into sine of theta into y. So these things are there for any fluid. Now if you look at the mu I model or the JFP model, whatever you want to call that, So for the JFP model, we have something. We have tau xy is just equal to eta dux by dy. Now instead of eta, we can write down in terms of mu. So you have mu into p divided by gamma dot into dux by dy. So now what we have is that, first of all, to see, since the velocity is maximum at y equal to 0 and it decreases as y increases, we know that dux by dy is negative. That's why you also get shear stress is negative. And this implies that our shear rate gamma dot is just equal to minus dux by dy. Okay. So, the gamma dot is nothing but the absolute value of dux by dy, which is just equal to minus by dy. So now if we put this in there, then you can see that tau xy is just equal to minus mu times p, which is of course the definition also. So if you then substitute for both p and tau xy, then you'll get rho bg sine theta into y is equal to minus of mu into rho bg cos theta into y. So now it's easy to see that everything cancels out. Rho b cancels out here, g cancels out, y cancels out. And so now you're just simply left with a final relationship that mu is just equal to tan of theta. So that means that in this flow, the friction coefficient is just a constant. And it just depends on this angle. So once you fix the angle, you have got mu. So, and even all the simulations, everything I showed you, that also has the same result. So let's just see, for the convenience, let's write this constant as mu 0. Just remember, mu 0 is nothing but tan of theta, and theta is a known quantity. So now if we substitute for the formula for mu, which is mu s plus mu2 minus mu s divided by 1 plus I0 by I is equal to mu 0. So now we have to rearrange it. I want to get an expression for I, because I depends on the velocity gradient. I depends on gamma dot. So I want to see what is I. From here you can clearly see, since everything else is constant, then the inertial number is also a constant. So what I'll do is, if I take mu s on the other side, divide throughout by mu2 minus mu s, and then invert it, then I will get 1 plus I0 by I is just equal to, So this gives us that I0 divided by I is just equal to mu0 minus mu s, and on the denominator you will have, since I have to do minus 1, so this will be mu2 minus mu s minus mu0 plus mu s. So I have taken 1 on the other side. So from here you can see that I divided by I0 is just equal to mu0 minus mu s divided by mu2 minus mu0. So this is what you get. So I is just given by a constant, and now we know that I is just equal to gamma dot d divided by p into p divided by rho p raised to the power of half. So this is taking I0 on the other side, is just I0 into so now I can replace gamma dot. I already know gamma dot is minus du x by dy. So here I have minus dux by dy, that's writing for gamma dot. I take pressure on the other side. Now pressure divided by the particle density, so I'll write that over there. So this is just equal to I0 by d into mu0 minus mu s divided by mu2 minus mu0, and then you have pressure, which is rho bg cos theta into y divided by rho p raised to the power of half. So remember, this is rho b, which is the bulk density. This is rho p, which is the particle density. The ratio of the two is just the solid volume fraction. So here again, I can simply write this as du x by dy is just equal to minus a into y raised to the power of half, where a is equal to, now this whole thing, I0 by d into mu0 minus mu s divided by mu2 minus mu0 into, now rho b by rho p is just phi, so then this is just nothing but phi into g cos of theta raised to the power of half. So this is what this, so it's basically exactly the same type of expression that we got for in our rapid flow result, but using a completely different formulation. You know that here you have, because of viscosity is a function of pressure, everything came in terms of the inertial number, and you can see that the derivation is entirely different, but the result is exactly the same. And so now if you just integrate this and put the relationship that ux is equal to 0 at let's say let's call this height as h, thickness of the layer is h as before, and so when we integrate this, you get ux is just equal to minus 2 by 3 a y raised to the power of 3 by 2 plus a constant, let's call it as c1. The boundary condition is that ux is equal to 0 at y equal to h. This is at the bottom of the layer, and that gives us that c1 is just equal to 2 by 3 a h raised to the power of 3 by 2. And so our final expression is again that ux is equal to 2 by 3 A into h raised to the power of 3 by 2 minus y raised to the power. Okay. So this is exactly the same thing that we had got earlier, the Bagnall profile. And in fact, if we had got something different, then obviously you will get, I mean, that means that the theory is wrong. If you don't get this result, that means that the theory is wrong. So this theory also gives us the correct result. And I think this is a good test for any theory, that at least for shear flow, it should give you the Bagnall profile. Now, if you look at this solution, you can see that actually it's written in terms of both the shear rate and, you can think of all these μs and μ2 as friction coefficients. But if you look at if you look at this expression for A, then you can clearly see that this μ0 has to lie between μ2 and μs. If μ0 is larger than μ2, you'll get negative value of A, and obviously there will be no flow. And if μ0 is less than μs, then again you'll get a negative value of A. And if you have negative value, means that the flow is going uphill. If ux is negative, that means that the flow is going upward, which is not possible. That's absurd. So A has to be positive. So for A to be positive, we must have that μ0 must be greater than μs and μ0 must be less than μ2. So this puts a limit on the flows, and so this gives us that μ0 must lie between μs and μ2. But we know that μ0 is just tan of theta, and so this essentially means that your angle theta must lie between theta s and theta 2, where your theta s is nothing but tan inverse of μs, and your theta 2 is equal to tan inverse of μ2. So μs and μ2 are friction coefficients, but then you can write a friction coefficient as tan of some angle of friction. So you can think of theta s and theta 2 as the two limiting angles of friction, and flow is possible only if the angle of inclination of your plane theta lies within this range. And that is also something I told you about last time, that you can get a stable flow only if theta is within a certain range. If theta is too large, let's say theta is larger than theta 2, then the flow keeps on accelerating and there's no steady flow possible. And if theta is less than theta s, then the flow simply stops because the friction overcomes the gravity force. Okay, so this is one simple thing, and so you get exactly what you get for rapid flow, but you get one small thing more, and that is you get this range of flows and a range of angles in which flow is possible. Now we can extend this solution to the case where you have side walls. So we can essentially do exactly the same problem, with frictional sidewall. So what this does is that it essentially gives some resistance, and so there will be, obviously the flow will no longer be just two-dimensional. So Ux will depend on both y and z. So we have this as it is. So this thing remains. So our geometry will be this. So I'm going to just copy this thing out. So the geometry is the same. This is the geometry when you look at it from the side. But let's say if you wanted to look at this from this side, then what it will look like is that you will have this is my base, and these are the side walls. Okay. So these are the side walls, and let's suppose that the material is flowing here. This distance is, this direction is y, and let's call this direction as z, and let's say that this width over here is 2 times w. Okay, and so let's also suppose that the wall coefficient of friction is mu w. Everything else remains the same. So again, our governing equations will be slightly more complicated. So, but let's start with the boundary conditions. And these are that at y equal to 0, you have tau xy is equal to p is equal to 0. In fact, I should put even, we expect there will be more than one stress component. So all the stress components are 0. At y equal to h, you just have ux is equal to 0. And at z equal to 0, which is at the middle point of this, you have d tau x, d tau xy by dz is equal to tau xz is equal to 0. So the shear stress will be 0, and it will be symmetric about z equal to 0, the other shear stress, other stresses. And at z equal to w, your tau xz is just equal to minus mu w times pressure. So this is what it will create some more stress in the system because of the walls, and this is the condition that the shear stress on the wall is just the coefficient of friction times the pressure acting on the wall. And if we write down the governing equations, again we are going to do a simple form for this. And our assumption is going to be that pressure is constant across the width, which basically gives us that P depends only on Y. It doesn't depend on Z. Okay, so this is one of the assumptions that we make. And so hence, you immediately get that P is just equal to rho Bg cos theta into Y, as we had got before. But now if you look at the X stress balance or X momentum balance written in terms of the stress, then what it gives us is that del tau xy by del y plus del tau xz by del z is equal to minus rho bg sine theta. So this is the extra term. This is the extra term that we get in the equation. And we are going to deal with this in exactly the same way that we dealt with in the case of the bin with frictional sidewalls, that we just average with respect to Z. So we're not bothered too much about the Z variation. So if we say averaging with respect to Z, the above equation, then what we'll have is that d by dy of integral from 0 to w of tau xy dz. So I'm integrating from 0 to w with respect to z. Plus, now if we just integrate this, we'll just have del tau xz by del z into dz is equal to, on the right hand side it's just a constant, so this is just minus rho bg into w sine theta. So now here we can define this as an average shear stress across the channel. So you will get W into d by dy of the average shear stress. Now here we can do the integral, because integral of a derivative will give you the quantity itself, and this is evaluated between 0 and w, and this is equal to minus rho b gw sine theta. Now we have seen from the boundary conditions that at z equal to 0, tau xz is 0, and at z equal to w it is just minus mu w into p. So that's what we can do. So we'll have here w is equal to w into d by dy into the average. Let me write down what is average stress. The definition of tau xy average is just 1 by w integral from 0 to w tau xy dz. And now we can write down tau xz at w is just minus of the pressure. So that will simplify things a bit. So this is just minus, the pressure is rho, the pressure is just minus, no, it's minus mu w into the pressure. The pressure is rho bg cos theta into y, as we have just seen, and this is equal to minus rho bg w into sine of theta. And so now you can easily get d by dy is equal. Okay. So, you get some additional term over there. So this expression looks exactly like, if we stop over here at this point, then this is exactly what we did in the first problem, but now we just get this one additional term. So by doing this, we are just making a small correction for what would happen if the sidewall friction was there. The shear stress will be modified by this. And you can notice that this frictional force is 0 at the free surface when y is equal to 0, and then it increases linearly with depth. And now if you integrate this, then you just get tau xy is equal to, I've made some mistake in writing this. Okay. Now when I integrate this, I will simply get minus rho bg sine theta into y plus mu w rho bg cos theta divided by 2w into y squared. So you get a slight correction to the shear stress. And now when I do what is mu, that is just tau xy by, let's say, minus tau xy by p, then this is just equal to rho bg sine theta into y minus mu w rho bg cos theta into y squared. Oh, I'm sorry. Why am I doing this? So when we divide by p, I have to divide this by rho bg cos theta into y, and this also by 2w into rho bg cos theta into y. So now if we simplify this out, this simply turns out to be, this first term is just tan theta like what we had got before, and now the second term is minus mu w into y by 2w. So this is now your new mu. So mu is now no longer constant. In the previous case, mu was just a constant. Now mu varies with y. And now if we substitute in the, supposing we call this as mu 0, let's call this as just mu 0, but this time remember that mu 0 is a function of y. So just like what we had got earlier, what we will get is minus dux by dy. This is nothing but I0 by d into, so I'm going to write down the same expression. Into y raised to the power of half. So this is what we had got last time, and we could easily integrate it because this was just a constant. But now mu 0 is not a constant, but it depends on y. It's a linear function of y. And we can sort of write this down through some simplifications. And this, if we write out let's call this actually as mu0 prime, just to be consistent with my notes. So just to remind us, this is a function of y, and let's call mu0 to be tan theta 0, tan of theta. So if we do that, then after some simplification, which I'll skip over, you'll just simply get minus dux by dy. Just remember, this is linear. This is just like some constant minus another constant times y. So that's what comes in here. So there will be just a y term that comes in addition. So you can, if you simplify this out, then you'll get a into y raised to the power of half, where a is exactly what we had defined earlier. But now you will also have b minus y divided by a plus y into a by b, where a is just equal to 2w into mu2 minus mu0 divided by mu w, and b is equal to 2w into mu0 minus mu-s divided by mu-w. So when you do a by b, then you just get this same thing, mu2 by, everything cancels out and you get the same factor. And then of course your a is exactly what was there before, which is I0 by d into mu0 minus, have I written it already over here? No. Remember, this is mu0, and which is a constant quantity. Phi into g into cos of theta raised to the power of half. So a is a constant, b is a constant, and small a, small b, and capital A all are constants. So we simply have to integrate this. If you go to the table of integrals, you'll easily find a solution to this. And then if you apply the boundary conditions that ux is 0 at y equal to h, then it's very easy to get an expression for the velocity profile, where now ux turns out to be, again, just in the interest of time, I'm not doing the algebra. So I said I'll write down what I did. You integrate and apply the boundary condition that ux is equal to 0 and y equal to h. And here you will just simply get ux is equal to a by b into a So this is the first bracket closed, and then you'll have plus 2 by 3 into y raised to the power of 3 by 2 into h raised to the power of 3 by 2 plus 2 into h raised to the power of half minus and this is the second bracket close. So this is what your expression for the velocity will be. So in the notes all the derivation is given, and it's easy to sort of see that if you put mu w equal to 0 in this case, you get back the Bagnol profile, and that is also there in the one of the things that is quite interesting over here is that since if you see this first thing that we have done here is that you could actually have a situation where our condition that is that mu 0 must be always greater than mu s and it should always be less than mu 2. But since since mu 0 is a function of the distance, it's quite possible that as as y increases, you see mu is decreasing. So if you look at this, mu is equal to mu 0 minus something. Now as y becomes larger and larger, your mu becomes smaller and smaller. So there may be a case when at some stage mu becomes equal to mu 0 becomes equal to mu s. So we can just say that maximum depth of the flow happens now. Let me write what I just wrote, what I just said. The condition for flow is that mu 0 prime must be greater than mu s. Okay, and we have got an expression for mu 0 prime, which is this expression. So we must have that mu 0 minus mu w into y by 2w must be greater than mu s if flow has to occur. If it becomes less, then the flow will stop. So this means that the maximum height, maximum value of y that we can have is when these two, the left hand side and right hand side, are equal. And so let's call that as h max. So mu 0 is minus mu w into h max divided by 2w must be equal to mu s. So that means h max is just equal to mu 0 minus mu s divided by mu w multiplied by 2w. And this is nothing but this is equal to B. If you see the definition of B, this is what it is equal to 2w into mu 0 minus mu s by 2w. So that means that if we have a system in which our height h, that is given over here, if this height h is larger than b, then obviously there will be some region of flow, and then there will be a no flow region because we are dealing with a Bingham fluid. So you will have this type of situation. Let's say if this height is b, and let's say if this height is h, Then you will have a Bagnol type profile over here, and then this is going to be a fixed bed. So this is what this is the sort of situation that we get. So in this case, instead of h in this expression, you have to put, instead of h, you have to put b. So in this case, the flow will not go right up to h, but it will stop at b. So just as the last equation, if I write down, the velocity field is just given as ux is equal to a by b into a to square root of a into a plus b tan inverse of y by a raised to the power of half minus tan inverse. Now instead of h, I have to just write b. So wherever there's h, I simply replace by b. It's the same equation as before. So this equation is the same as this equation. Only thing, wherever there is h, I have to replace this h by b, and that's what I have done. So here we are seeing how this JFP model predicts the formation of fixed beds and all, as is seen in experiments. If you do experiments, you will see this type of behavior, but this cannot be predicted by the kinetic theory rapid flow models. Okay, so thank you. I'll stop, and I will see you tomorrow morning. Okay, bye bye.